All right, so welcome everyone. Thank you for joining us for another fun and exciting Lunch and Learn lecture. For those of you who don't know me, my name is Jillian LeClaire and I work in the Florida Tech Office of Alumni Affairs. And we are excited today to talk about space robotics. Joining us is a faculty member, Dr. Markus Wilde, who is going to tell us all about this emerging field. And I know nothing about it, so I am very excited to learn lots of fun things. So for those of you who haven't been to a Lunch and Learn lecture before, the lecture is about 45 minutes long with about 15 minutes at the end designated for questions. But if you think about questions as we go through the lecture, feel free to type those in the chat box, and then we can circle back at the end, and Dr. Wilde will answer those for you. As I mentioned before, my only request is to leave your microphones on mute throughout the duration of the lecture so that we don't get any of that pesky audio feedback. And to get a better idea of who's joining us today, I'm going to launch a quick poll. And I do this before every Lunch and Learn lecture just to kind of see if you attended Florida Tech, when you were here, what you studied, and what you're up to now. So I'm just going to send that out real quick. Take a moment, please, to fill that out. I'm sorry you guys can't see all the results as they come in. I'll share them once we're done. But I just love seeing all the bars go as you're submitting your responses. All right, I'll give you an extra 10 seconds to get your votes in. All right, and I'm going to end the polling in 3, 2, 1. All right, so I'm going to share the results with you guys. So it looks like we have the largest representation from the last decade. So young alumni showing up to learn something cool. And then we have 24% from the 80s. So thank you all for joining us, no matter when you attended Florida Tech. And 57% of the attendees studied engineering, 28% science, 15% business, a few aviation folks, and a few liberal arts. Where do you currently live? Overwhelmingly on the East Coast. And we have a few international. If you guys live outside the US, go ahead and type where you're from in the chat box so you can see where you're joining us from today. And have you attended a Lunch and Learn lecture before? Wow, 61% said this is your first one. So thanks for joining us. I hope you love it. And 35% have been to a couple. And the fun question, I always have to add a fun question at the end. If you were offered a seat on an upcoming commercial spaceflight, would you go? Assuming that it's free, of course. And 74% said, heck yeah, would definitely go. And 26% said, no way, it's too risky. And I would have voted that as well. Okay, so I'm going to stop sharing that. Thank you guys for participating. So now to introduce our wonderful faculty member, Dr. Markus Wilde received his Master of Science in 2008 and his PhD in 2012 from Technical University of Munich, Germany. He was accepted into the NRC Research Associateship Program in 2013 as a postdoctoral associate at the Spacecraft Robotics Laboratory at the Naval Postgraduate School. In 2014, he joined the faculty at Florida Tech. He teaches undergraduate and graduate courses in the design of aerospace systems, spaceflight mechanics, spacecraft mission engineering, aircraft stability and control, and spacecraft robotics, As the director of the Orion Spacecraft Robotics Lab at Florida Tech, he leads a research team investigating autonomous and telerobotic capabilities for rendezvous and capture of space objects, robotics technologies for on-orbit servicing and debris removal, which we'll be talking about today, and novel simulation capabilities for space robotics systems. And with that, I will turn it over to Dr. Wilde.
Hey, thank you. Let's just see if we can work this Zoom magic again. Yay. So I hope you can all see the slides. After doing this for like 16, 18 months, I think I'm going to get another PhD in Zoom engineering. I was invited to this forum, and I was happy to accept because I think the topic that I'm going to discuss a little bit, the whole idea of space junk, on-orbit servicing, and the robotics technologies we need for that, is a very hot issue, is going to get hotter and hotter as we go along. And as any really important issue in spaceflight, it does not receive the attention that it should get, especially from funding agencies. So that is something that has been seen a lot in the past, right? The stuff that really needs to get done is not getting funded, and money is spent elsewhere. So first thing, when we talk about space, right? So most people think this of space: stars, emptiness, and a UFO zooming by every now and then. That's the common perception of space, right? We call it space because there's a lot of it. But when you look at the current statistics, this is about 2 months old. We right now have about 4,100 active satellites in Earth orbit. The vast majority of those, 3,300, are in low Earth orbit, right? So like somewhere between 200 and maybe 1,000 kilometers altitude. Then we have roughly 560 up in geo orbit. That's your classical TV satellites and your Sirius XM satellites and stuff like that. And the rest is just sprinkled somewhere in between. A bunch of them are in medium Earth orbit. That's your navigation systems, your GPS, GLONASS, Galileo, and the Compass Beidou system. And then some small stuff in highly elliptical orbits. And now you would say, hey, we got plenty of space to deal with. 4,100 satellites is not a problem. And this is kind of how it developed. So you see the stuff in elliptical orbit hasn't changed much over the last 15 years. MEO hasn't really changed that dramatically. GEO is almost linear growth, but this is what happened in low Earth orbit over the last 15 years, right? So we went from about 400 satellites in low Earth orbit in 2005 to 3,300 satellites nowadays. And you almost see two step changes. So here we saw a dramatic increase in satellites due to CubeSats, right? So now everybody and their grandma is building satellites and launching them. And since 2019, we've seen the Starlink satellites being deployed, which dramatically increased the satellite population. Basically, they doubled them. They doubled the number of satellites in space within roughly 2 years. And now you would again say, well, why is that a problem? Why do we care? Well, it's simply how we do this stuff. So let's just imagine you were building a fancy, highly customized car, spend a lot of money on that. And then you just wait until you run out of gas, your battery's dead, you have some kind of system failure, your radio is dead, or the ashtray is full. And then all you do is you push it to the side and you walk off, right? Doesn't seem like it's making a lot of sense, but this is exactly how we do spaceflight. We build our satellites, we launch them, we use them for as long as they last, and then we just walk away from them and pretend we don't have anything to do with them. And that is the problem behind space debris or space junk. So space debris is in general defined as any remains of spaceflight activities. So any non-operational object, right? So any old satellite that we just dropped, or any kind of mission-related debris. So every time we do a rocket stage separation, we produce debris. Or it could also be stuff that happens when we use the ISS. I mean, tools have been lost. Astronauts have lost gloves and stuff like that, right? So we've had overall more than 8,000 launches, or around 8,000 launches over the history of spaceflight. We've had more than 250 explosions in space. Some of them just happened by accident because a battery ruptured or a tank ruptured. Some of them were intentionally caused by anti-satellite missile tests. We use solid rocket motors in space quite a lot. These solid rocket motors, when the exhaust gases basically start condensing in space, they create small debris objects. We've had nuclear reactors in space, and at the end of the life, we dumped the coolant core, the core coolant, and that was then all of a sudden space debris objects. And stuff like that happens all the time. And the problem is we don't get rid of it. So we only have drag and some solar radiation pressure, and also the gravity of the sun and moon that can actually change the trajectory of space debris and maybe direct it into the atmosphere, or maybe get it out of Earth orbit. But that is a very inefficient process. So, and then again, the big problem is what humans are really bad at is to judge energy. And if you just get hit by a 1 centimeter debris piece, it's basically like being struck by a falling anvil, right? So the pure fact that these particles are moving at orbital velocities, as soon as they hit something, they cause major destruction. And in general, we say that if anything larger than 5 centimeters hits a spacecraft, for example, the ISS, then we're going to have a major fragmentation event and we lose the spacecraft that's being impacted by it. And then this spacecraft is going to be blown into thousands of other pieces at that size range. And then these pieces may also hit other spacecraft. And all of a sudden we're having a chain reaction, which is typically called the Kessler syndrome after a NASA researcher. And we're still not sure if we're already in a Kessler syndrome kind of situation or if it's just on the horizon, but definitely this is a real problem. And depending on what projections you believe, it could mean that we have to stop spaceflight for around 50 years because it's getting too dangerous to fly anything, especially anything with a crew on board. So these are our real problems. Here we see the current number of objects in Earth orbit. And you see that there is about 22,000 objects that are being tracked. Remember, the objects that we can track are typically larger than 5 centimeters. So there's a lot of objects that we have no actual clue where they are and how they fly around. We just do statistical modeling on them. But around 22,000 objects are actually actively tracked by NORAD. And you see that there have been a few step changes, right? So in 2008, 2007, 2008, that was a anti-satellite missile test run by China, which caused a giant step change in debris. And then in 2010, we had a collision between an Iridium satellite and a Russian satellite, which caused another step change in debris. And that stuff is not going away, right? So you saw it increases and then it stayed. It never subsided again. And now to put that stuff into perspective, let's look at the mass that we have up there, right? So when you look overall, we have about 8,500 tons, metric tons of debris objects up there. And again, as a reference, that is about 20 Boeing 747s or one warship that we have in orbit right now as debris. And as you can also see, that number is steadily rising. It's not in any way, shape, or form decreasing. It's just going to increase more and more and more. And the fact that we're now launching hundreds of satellites for communications constellations will not help in the long run. So what can we do, right? So there's different concepts of actually doing space debris removal. There's all kinds of fancy concepts, right? We could use space lasers to push stuff out of the way. We could use bolas, harpoons, nets, all kinds of stuff to grab things. We could use robotic arms. We could use tentacles and all that stuff. And the dirty secret is none of these really work. There's a Japanese company, Astroscale. They are testing what's called ELSA-D. It's a space debris removal demonstrator. They basically use adhesives or magnetic connectors for capturing debris. ESA is going to fly Clear Space 1, which is going to use a large robotic mechanism to capture stuff. But space debris removal is insanely hard. It has not really been successfully demonstrated with any kind of operational context. And all the systems so far that have been tested actually risk creating more debris when we remove a specific debris object. So maybe we should actually, instead of creating more space debris, we should make sure that our spacecraft do not become space debris. And that's bringing up the whole area of on-orbit servicing. So on-orbit servicing is basically maintaining, repairing, upgrading spacecraft in orbit. So what we can do up there is we can inspect them, right? So we can fly up to a satellite that's not functioning properly, inspect what's going on, and then instead of giving it up, maybe come up with a repair plan. We could refuel spacecraft in orbit for some of those where that makes sense. Not every single spacecraft makes sense to be refueled. We could repair them, we could upgrade them in order to increase the capabilities and have them a longer functional life. We could maneuver them around, either in order to increase their commercial utility or to move them out of their orbit at the end of their life so they don't become actual space debris objects. And then what that gives us would be, we could have more flexibility in actually designing and operating spacecraft, because typically the useful life of a satellite is 15 years, and it's very hard to judge in what the communication satellite landscape is going to look like in 15 years. So we could design the satellite to actually provide maximum utility for the next 5 years. And then down the road, if the conditions change, if the customer demand change, we could send a servicer up to change the satellite in orbit, and with that have more commercial utility with that. That would increase the capability of the system lifetime of the satellite, would overall increase the return on investment, and it would also basically usher in an era of sustainable spaceflight, because we would ensure the enduring usability of the orbital environment, because space debris, the existing space debris is still going to be a problem, but we wouldn't be producing new space debris every few days by decommissioning a satellite without deorbiting it, as we do right now. And obviously there's nothing in spaceflight that hasn't really been done. So the big thing about on-orbit servicing was the Space Shuttle, right? The shuttle was from the get-go designed as a servicing platform. It had really nice orbital maneuvering capability. It had a very large payload bay that actually even allowed it to return satellites from space to be repaired on the ground and launched again. And that was done a few times. It had a mixed crew of astronauts and engineers on board, had a robotic manipulator. So the Space Shuttle was from the get-go designed as a servicing platform, and it did its job marvelously well, right? So there were a lot of successful servicing missions, most notably, obviously Hubble, which would have been a complete failure for NASA in 1991 had it not been for all the repeated servicing missions. And then obviously the assembly and the maintenance and resupply of the ISS is another success story when it comes to the Space Shuttle. Other than the Space Shuttle, we have not really done on-orbit servicing since the shuttle was retired. One big caveat is what's currently going on in GEO, because Northrop Grumman flew 2 mission extension vehicles, MEV-1 in 2020 and MEV-2 in 2021. And what these things are doing is they are latching onto geostationary communication satellites, and they're taking over the station keeping function of the satellite's propulsion system, so that the satellite can remain on station longer, and with that increases the useful life. And at the end of the mission, these vehicles are then going to move the GEO satellite into a graveyard orbit so that they don't become a collision hazard or debris object on GEO. So on the lower left, you see what that looks like, right? So you have the large communication satellites here, and then you have the relatively small MEV attached to it. It's typically, it's grabbing the nozzle of the apogee kick motor. And then there's also the Mormon ring, which is basically how the satellite was attached to the launch vehicle. And these are actually on the upper right, these are actually images of a GEO satellite taken by the MEVs from basically directed towards the Earth, right? So these are very special pictures because that's the first time we've had images like that taken from one spacecraft to the other on the GEO belt. So this is a great capability, but it's not yet full-scale on-orbit servicing, right? So these MEVs at this point, they don't do any kind of robotic manipulation of the target. They don't do any kind of component exchange. They don't repair anything. And up to this point, there have been 2 demonstration missions of full-blown robotic servicing. So the first one was the Japanese ETS-7 in 1997, which happened in low Earth orbit. They had a custom target object that they brought with themselves. And then they practiced telerobotic and automatic capture of that object. And they also had successful exchange operations of what's called orbital replacement units. 10 years later, DARPA followed suit, and they basically did more or less the same thing. Just this spacecraft was more automated, was highly autonomous, and they exchanged a full flight computer, they exchanged a flight battery, and they also did a cryogenic fuel transfer. And then nothing happened for a long time, and now NASA, they ran the robotic refueling mission on the ISS. And that was a preparation for the upcoming OSAM-1. So it used to be called Restore-L. Now it's called the mission OSAM-1. It's supposed to fly in 2022, unless that slipped. And what they're going to do is they're going to grab an old Landsat satellite, Landsat 7, which was not designed to be captured, and it was also not designed to be serviced. And they will actually refuel it, relocate it, and redeploy it. So that's going to be a major milestone in the area of on-orbit servicing. And DARPA is also going to do a very similar mission, but up in GEO. So the idea is that you grab resident space objects, so a GEO satellite, and then you do autonomous capture, inspection, relocation, repair up in GEO. So with that, there will be demonstrations for full-blown on-orbit servicing operations in both LEO and GEO. And after that, whether it's going to catch on or not does not so much depend on the agencies. It depends more on commercial customers, whether they actually want to take that. So in general, this stuff is insanely hard with 2 major areas. So there's the general challenges of flying anything in space, right? So rendezvous is a challenging prospect because of the orbital dynamics, because of how hard it is to do relative navigation in space. And also because servicing or debris targets are not just going to sit there and wait for you to come, and they won't tell you their position, and they won't have stable attitude. So we will have to be able to approach tumbling objects, which is really tricky. Then capture is tricky because as soon as you touch an object in space, it's going to start changing its tumbling motion dramatically. So we really have to deal with the multi-body dynamics up there. And we also have to find capture mechanisms that are able to grab something in space that is not designed to be grabbed, which is also a challenge. And then we have to make sure we test and validate all that stuff on Earth. So we have a high level of confidence that it's going to work before we fly it. Otherwise, we just risk creating a giant cloud of space debris when our servicer spacecraft collides with the client, which also nobody wants. And then there's robotics challenges, right? Robot arms are fun on Earth, but in space they're hard. So having a multi-degree of freedom robotic system operating in space environment with the associated temperature swings, lubrication problems, radiation problems is a giant challenge in itself. Then space hardware, satellites are not necessarily built to be manhandled, right? So handling delicate space hardware without breaking it is a challenge. If we try to repair a failed spacecraft, there is a lot of flexibility and adaptability involved. And I encourage you, look up on YouTube, look up some videos of the shuttle missions to rescue some of these satellites like Westar and Palapa B2. A lot of times it was astronauts guiding that stuff into the payload bay, either with the manned maneuvering unit or just with their hands, because the robot arm couldn't really capture these things. So grabbing something in space is insanely hard. The work environment is unstructured, which makes it hard to use machine vision. Spacecraft surfaces are highly reflective, which again makes it hard to use machine vision. And overall, operating this kind of stuff in space is really tricky. And once we manage that, once we actually master all these technologies, the cool thing is we can not only remove space junk, we can not only do on-orbit servicing, but now we can even think about, hey, why don't we do really in-space assembly? We've demonstrated with the ISS, but there's way more to do, right? So We cannot launch spacecraft of arbitrary sizes in our launch vehicles. So we have to do in-space assembly. We demonstrate that with the stations, but as we go further into the solar system for human exploration missions, we will have to do in-space assembly, in-space refueling. If we want to use something like space-based solar power satellites, we will have to do in-space assembly on a scale that is absolutely unprecedented. And all these technologies here are closely connected to the challenges we have to overcome for debris removal and on-orbit servicing. And another thing, asteroid exploration and mining is also closely connected to that, because an asteroid typically has a gravity field that's so weak that you don't land on the asteroid, you basically dock with it. And that recently has been demonstrated by the JAXA's Hayabusa 2 and also the OSIRIS-REx mission. And if you really want to go out there and start mining asteroid, then we also need to defeat a lot of the challenges that I just laid out for on-orbit servicing and space debris removal. So all of these areas, all of these emerging areas of robotic space are closely connected, and they all kind of have the same problems that need to be overcome. So, and that's where we at Florida Tech and the Orion Lab come in. The Orion Lab is an experimental facility that is really tailored towards doing research in on-orbit servicing. So we have a lofty vision, right? So we want to become a leading research lab for space robotics, rendezvous proximity operations, and a go-to partner for US industry and government. And our mission statement, this mission statement is a little bit tailored towards Space Force, but what we want to do is we develop, implement, demonstrate prototype technologies for guidance navigation control, robotics, and mission ops to turn small satellites into the PT boats of the 21st century. If you don't know what a PT boat is, I ask you to request your money back for the humanities classes and to look it up on Wikipedia. So, and overall, the technologies that we're looking into are for space asset protection and defense, space object inspection, the resolution of anomalies on spacecraft, on-orbit servicing, in-space assembly, and debris removal. And how we do this stuff is we have a lab that's at the Applied Research Laboratory. I don't know if you remember that, but it's about 2 miles north of campus. And in there, we have a nice large workspace, almost 10 by 10 by 3 meters, where we have spacecraft maneuver simulators. We can simulate the lighting on orbit, and we can track all the objects and do closed loop controls. So this is what that looks like. So we have 2 simulators in here. One is a maneuver kinematic simulator, which basically just represents the geometry of relative motion between 2 spacecraft. Currently, we have a target satellite equipped with solar panels and a nozzle and stuff like that, sitting on one mechanism, and the other one, the pan-tilt mechanism that is empty in this picture, actually has a model of a chaser satellite on it that is equipped with a bunch of different cameras, capture tools, and things like that. Then back here, we have an air-bearing table, which is an optical bench with a 12 by 6 foot glass plate on top. And on that one, we can float small satellite simulators that I'm going to talk about more in a second. We have a really nice LED light that can represent the orbit lighting conditions. So we can saturate cameras, we can overpower LiDARs with the light source, just as you would find on orbit. And we have OptiTrack cameras all around. So OptiTrack cameras are a visual tracking system. So our vehicles in the lab are equipped with little infrared reflectors, and the cameras basically triangulate the location of these infrared reflectors, so we know the location and orientation of every single object in the lab down to 1/10 of a millimeter and to 1/10 of a degree in accuracy. And that's what we use to test some of the technologies. These are our 2 air-bearing vehicles. We have a chaser spacecraft called Bob, and we have a target spacecraft called Charlie. For all intents and purposes, they are fully equipped spacecraft. They have onboard, they are fully autonomous, right? So they don't have any lines connected to it or whatever. They run, they have thrusters for propulsion, custom-made nitrogen thrusters. They both have nitrogen tanks running at 2,800 PSI on board. They have an onboard computer. They are fully wireless. And the chaser spacecraft has, this is a picture with a capture tool on board. We're currently outfitting it with a robotic arm for refueling experiments. And the target object, in this case, it's a bit hard to see, but it has a segment of one of these Mormon or launcher adapter rings attached to it. And currently we're replacing that with a refueling receptacle so we can then transfer liquid from the chaser onto the target in experiments. And these things are running on air bearings. There's these little blue dots underneath. So what happens is we run nitrogen about 100 psi through these air bearings. They create a very thin, a few micron thick film of air under the vehicles. And with that, friction is no longer a problem, and they actually start moving like real spacecraft, right? So if you nudge them, they will start going and they won't stop until they run into something else. And this allows us to test spacecraft control systems. This allows us to test robotics control systems, contact dynamics, all that stuff in the lab. So, and our research and development thrust or topics, we go down two directions. So the first one is we're continuously developing our testbed technologies. So we're making the testbed better and better in order to get more fidelity in our simulations, more fidelity in our experiments, and also to reduce the uncertainty in the system, right? So we want to make sure that we are able to characterize these systems better and better, so that when we fly something in actual spacecraft, there's no more surprises there, right? Having a surprise with a expensive space mission is always a bad thing. And we're developing small sat technologies. So we're doing rapid development, rapid prototyping, rapid testing of different technologies on our test bed. So somebody comes up with a certain new algorithm for processing sensor data. We just quickly implement that, put it in the lab, test how does it work under different scenarios, different lighting conditions, stuff like that. Somebody comes up with a new control law, we just quickly test that out. And that is the beauty of having this kind of lab on campus, because it allows us, so faculty researchers and students, to just quickly try stuff out, test it, see if it works or not. So, and here are some examples of projects that we have ongoing. So the overarching theme is to enable something like this. So this is basically the concept for a Piggy-Back inspection repair satellite. So you would launch a large spacecraft, large spacecraft, and then you have a bunch of these attached to the skin, almost like remoras attached to a shark, right? So they would always be there. And then if the large satellite has any kind of malfunction, you would deploy them to inspect the satellite, figure out what's going wrong, and then maybe execute some small repairs on that. And we ran a bunch of capstone senior design projects. So one of them built the satellite prototype called Cerberus. Here you see a cat shot of that. It's equipped with robotic arms. It's equipped with thrust vectoring systems. And the year later, we figured out, hey, what happens if the batteries and the gas tank of that thing are empty? So we also designed a docking station called Typhon for that. And Typhon is able to capture Cerberus using these capture prongs on the front of the vehicle. Basically pull it in, and then there is like quick disconnect fittings for electrical and gas connections, so we could recharge the satellite. So, and that's kind of the idea behind these small spacecraft, right? So you would have one or more of these docking bays basically attached to the large satellite. The Cerberus vehicles are attached to these docking bays, and then you just use them as you see them fit, right? Whether it's for inspection purposes, repair purposes, or also for defensive purposes, because you detect some other small spacecraft that's creeping up to your large GPS satellite or communication satellite. All of this stuff could be done with these kind of things. So then the building up on that was the idea, hey, what if we use a bunch of these small satellites, so a swarm of these small satellites, to actually go after a large space object that's tumbling, and to identify it, characterize it, and then also stabilize it, so we could then execute debris removal or on-orbit servicing missions. So that's the big topic that we're working on right now. So how can we accomplish collaborative or cooperative relative navigation around the vehicle for swarms? So we have this idea that we have a bunch of these small satellites all equipped with cameras that would basically fly around a large space object and then kind of build up such an ad hoc tracking system similar to our OptiTrack system, so that they would then characterize the motion of the target and also track other small spacecraft that approach this target object. So we're working on that in the lab. We're also working on using point cloud-based relative navigation in order to determine the geometry and also the motion status of the target object. So we started using a Microsoft Kinect camera, right? Because we figured, hey, if it's good enough for video gaming, it must be good enough for space. And we ran experiments in the lab. So we used the kinematic simulator gantry, right? So we had the camera on our chaser vehicle. We had our target object. And then we just used the color video we got and the point cloud we got in order to determine how much has the target rotated over time, what is the difference between two consecutive frames, and then we were able to come up with the attitude solution, also a position solution for that. And that was a master's thesis that was finished, I think in 2018, as far as I'm concerned. And that was great because we were able to show that within our lab, we were able to get like 1 to 5 millimeters accuracy. And that's something you can work with when you actually start approaching it. Now we're going further into it. We're now combining machine learning with this. So we're using machine learning algorithms in order to do spacecraft feature recognition. Because you can imagine if you go after a large satellite with solar panels and antennas, the last thing you want to do is you want to fly through any of the solar panels. And you also need to figure out where on the satellite are you actually going to capture it. So in order to do that, we either need humans to tell us which features to go after and which features to avoid, or we somehow train our satellite to do it itself. So that's what we're doing here. We're using machine learning algorithms to be able to identify solar cells, antenna apertures, body panels, thrusters, so that we can guide our chaser spacecraft towards the right features. And this is currently being done as a master's thesis, supported a lot by undergraduate students, and we were able to get some funding for this from AFWorks through an STTR. And we actually applied for a phase 2 STTR, and so far we got a lot of support from them. So hopefully that's going to take off in the next few months. And then that's going to preoccupy us for the next year, probably. The big challenge is machine learning, right? Machine learning, I like to call it machine guessing because there's not really learning involved. So you just feed the algorithm with an immense amount of pictures until it understands that a certain combination of pixels represents a solar array or a antenna. And the problem is, if you go after cats, dogs, and stuff like that, there's millions of pictures you find on the internet. But if you go after satellites, we were highly taxed with just finding like 1,500 pictures. And then some of my immensely brave undergraduate students spent weeks and months labeling these pictures in order to enable the machine learning. So training these systems is a challenge for spacecraft. And then running these systems is also a challenge because of the lighting conditions on orbit, and also the fact that most spacecraft are covered in highly reflective MLI, which also doesn't make anything that has to do with machine vision any easier. Then once we have that, we're also looking into how do we approach a tumbling spacecraft. We use different approaches for that. So one of my early PhD students looked into using sliding mode control in order to approach a tumbling target. What we're currently doing is we're looking at artificial potential field guidance. So you would have repulsive potential field sources on like solar arrays and things like that. You would have attractive field sources close to the capture points. And then you would also put repulsive field sources on other chasers in your swarm. And then magically, they're going to self-organize and follow kind of the potential gradients and attach themselves to the target spacecraft. And what we're doing right now in the lab with some funding by AFWorks, but mostly a lot of grit from undergrad students, is to refine these algorithms to find out what are the drivers, what parameters do we have to adjust in order to minimize the delta V, the overall delta V, minimize the maximum thrust, minimize the impact velocity, And we're currently running massive MATLAB simulations that really try to map out the trade space here. And that's what's currently going on in the lab until the computer smokes. Then we're also using at very low level controls, limit cycle controls for our air-bearing vehicles, because the thrusters that we have are not really the best on the planet, and they have large uncertainty in the thrust levels that you have. You see that here, there's a lot of fluctuation in here, certain onset time issues. And integrating that into PID controllers is a bit challenging, so we built a low-level bang-bang controller that at least maintains our satellite within a certain bounding box. That was a master's thesis 1.5 years ago before COVID that accomplished that. Currently, so now what we also need for these spacecraft, we need thrusters that, number one, pack a lot of punch, number two, are inherently safe. So they don't have any pressure vessels and stuff like that. So we figured, hey, why don't we build a thruster that basically ignites small pellets of solid propellants and then ejects the gases through like a bunch of different nozzles. And this is actually right now an ongoing capstone design project supported by a master's student to develop a prototype of that. So maybe next year around this time when we talk, then I hope we have this thing tested in our little dirty vacuum chamber. And that would be really cool. And actually, I talked to some Air Force guys yesterday. They seem to be really interested in this kind of stuff. So that's a promising venue that we're going after at this point. Sorry, my phone. And then we're also interested in how can we capture something. So how do we go away from the typical robotic manipulator, robotic gripper in order to grab something in space? And we're trying to do all kinds of weird stuff, like glues, like capture tools inspired by nature. So far, we haven't really found the silver bullet, but a capstone design project that recently concluded, they built a capture tool based on capacitive discharge welding. And that was pretty cool. So basically what happens is you have this capture tool, right? So you see these 3 welding prongs here, and they will basically be pushed against a space debris object. And as soon as they are pushed in far enough, they will actually close the contact. We're gonna have an arc, and the prongs will weld themselves to the target object. So you could have our parent satellite here with the tool that was called DISARM, and it would basically weld itself to a space debris object. And then if we did our job right, that weld is strong enough to allow us to detumble it and then potentially do deorbiting maneuvers for this. And the prototype is sitting in my lab. And now I'm looking for grad students that actually will test this thing in a vacuum chamber, test it on a dynamics test bed. But this is a cool project, and we have a really nice prototype that we can use for future research in this area. Then I mentioned our refueling project, right? So the idea is, why don't we turn spacecraft refueling more into air-to-air refueling? So instead of having one spacecraft grab another one, latch itself onto it, and then refuel it, why don't we have them fly in formation? One of the spacecraft deploys a robotic boom. The other one basically flies into this boom. And we got some initial funding by Florida Space Grant like a few years ago to start developing this. And now we're turning it further. We're actually now prepping the experiments for that. We're combining machine vision with this. We're combining a lot of concepts from robot control so that we can make this happen. And the actual refueling experiments are going to start in the next few weeks once we iron out a few more bugs on that system. We're also looking into using flexible continuum robots to capture tumbling space debris objects, right? So we ran a bunch of experiments in our system where we use these kind of tentacle robots to capture a tumbling spacecraft. We partnered with Clemson, with Ian Walker from Clemson University on this a few years ago. Also had some promising results. And yeah, and so we're just going down the technology chain here. We're also looking into using virtual reality user interfaces in order to command our capturing spacecraft. So instead of basically telling the spacecraft, hey, move forward by a certain amount, we would basically just click and drag into a certain location in space, and then our spacecraft would automatically execute the maneuver sequence to get there. And another thing that we're really interested in is what if the human has to take over control? What if a engineer on the ground actually has to control the spacecraft during a certain part of the mission? How do we defeat the time delay that we have in the communication chain? And we're currently trying out different displays for that have a predictive element for time delay, and we're actually testing these with our quadcopter test bed. So we have students remote controlling quadcopters in our lab through multi-second time delay, which can sometimes result in substantial hardware damage, but hey, it's a lab. So, and sorry for the tour de force. I just quickly wanted to give you an overview of the overall problem that is associated with space junk and on-orbit servicing, and some of the stuff that happens here at Florida Tech in order to defeat these things. I know it was fast, but hey, if you saw anything that you want to talk more about, obviously we have a few minutes for Q&A, and you can always call me, send me an email, look at our lab website. That's always open. And if you're in town and you want to see the lab, just give me a call, and we can also make that happen. So, and with that, I was told I had 45 minutes, and I had it exactly down to 45 minutes.
Well done. It was on the dot. Thank you, Dr. Wilde, for that spectacular overview. We do have a handful of questions in the chat. Would you like me to read them out for you?
Yeah, I think that's best.
Okay. So Larry Pollock asks, this seems to all come back to cost, and the limited budgets, for example, NASA or even private industry, have historically gone to furthering space exploration and not debris cleanup or design for on-orbit servicing or disposition to deeper space. Where is the graveyard orbit? Beyond GEO?
So the typical graveyard orbit we talk about is like 250 kilometers above GEO, but there have been two others set aside. One is between medium Earth orbit and GEO, and the other one is between LEO and MEO, but they are not typically being used at this point. So, well, and the cost problem, yeah, especially space debris is a cost problem, because who's going to pay for cleaning up orbits, right? I mean, on-orbit servicing is relatively simple. If you are a customer and you want your satellite repaired, you're going to pay for it, right? So, and that's also the business model behind the MEV, the Northrop Grumman Mission Extension Vehicle. Intelsat is paying them for the life extension. The debris thing is a giant problem, because obviously nobody feels responsible for paying. And in the end, if you ask me, I mean, there's now proposals to like add a launch tax or something like that, so that there is some money that's going into a common fund. If you ask me, I think that's a government job. I mean, air traffic safety is a government job. Maybe space traffic safety is also a government job. I don't know. So
you kind of delved into Lillian's and Anderson's questions. They asked, who's responsible? Are countries responsible, are accountable for their own space debris that they leave behind? Would there be a global governing body? And then they talked about
in general,
Space
right?
Force.
There's something called the Liability Convention, and it's a little bit old, from the late 60s, but in the end, it clearly states that a government is responsible for its actions in space. And if a US satellite rams a Russian satellite and blows it to parts, then in the end, the US government is responsible. So I don't know how we get around that, but somebody needs to pay for it. And usually governments have the biggest purses. So, yeah.
So only time will tell.
Yeah, and I mean, that's how international stuff works, right? We always have a treaty after something bad happened.
So after all the highways are clogged with the broken down cars, that's when they'll.
That's how we do things.
Hop on it. Gotta love that. All right, let's see what else we have. John asked, might sound simple, but would a large, quote unquote, bag traveling at a slower speed and orbit paths work for large debris cleanup instead of specific robot controllers?
It may work for like the really small particles. The big problem is just, right, stuff in space goes every which way. I mean, if you have this bag and you go after something that's in the same orbit as you are, you're going to be golden. But as soon as something flies in on a different orbital plane, it's going to collide with your bag at speeds of, I don't know, maybe even 8 kilometers per second, and your bag is just going to be in pieces. So it's tricky. And going after big objects is actually, in some respects, easier, but it's more worthwhile, because if you grab one of like a multi-ton space debris object, like a 6-ton satellite, then you have one object you're going to grab, right? So it's more manageable, and you remove 6,000 kilograms of potential space debris from orbit before it becomes small. And I mean, the small stuff is hard. It's hard to track. It's hard to fly to. It's going every which way. It's hard to keep under control. So I think going after the big stuff makes more sense than going after the small stuff.
James asked, and I'm not sure what this was in specific reference to, but he said, why not use good old monopropellant thrusters? I think it was on one of the last slides.
The idea was that if you have any kind of monopropellant thruster, you still have basically a pressure tank for the propellant. And if you want to fly anything as a piggyback payload, if you want to launch cheap, then usually the guys flying the primary payload object to you having a explosion source on that same launcher. So that was just the concept. If you wanted to fly these things, not as CubeSats, but as relatively small satellites, and you want to launch cheap as secondary payloads, then having any kind of pressure vessel on board is probably a problem. And that's why we want to work around that a little bit.
Simon asked, will we see the recording? Yes, I'm going to email everyone. As soon as Zoom sends me the link, I'll share it with everyone if you want to rewatch. And everyone said fantastic presentation. It's packed full of useful information. So everyone's saying thank you very much. Let's see. Pretty asked, would it be possible to reuse some parts of the junk?
I didn't put that in there, but a few years ago, I submitted a proposal to NASA that was doing exactly that. So I was proposing an in-space recycling facility that was basically gobbling up junk on one side and grinding it into feedstock for 3D printers. NASA said, I mean, it was going after NASA NIAC, the Innovative Advanced Concepts, and the idea was not crazy enough for them, so they didn't fund it. But that was an idea, because I mean, we saw it. It's 8,000 tons of material, and it's space grade material. It's high quality stainless steels, aluminum, titanium, electronics that include a lot of silver and gold, right? So I think that is something we should consider in the future, to use this stuff to build things in orbit.
Mike asked, has there been any effort so far at a federal level to create a consortium or cooperative allowing people to work together globally or nationally on this?
There's a lot of international stuff, mostly on the regulatory side. So how do we do this in order to prevent creating more debris? There is an industry consortium called CONFERS, which is basically developing on-orbit servicing technologies and things like that. And Florida Tech is a member of that. And there's a lot of efforts towards standardization of surface markings, of navigational beacons, stuff like that, in order to make this a reality and not just a research project. And obviously everybody's working on that. The Europeans are doing a lot in the area of space debris removal right now. The Americans are doing a lot in the area of on-orbit servicing, and obviously everybody's talking to everybody else. So there is a lot of effort. It's just the research development on that side is moving slower than the problem is growing, right? So that's a problem.
I think we have time for 2 more quick questions. Joy Patterson asked a fabulous question on the sustainability side. How would you dispose of the junk once you capture it?
Depends. So if you're in low Earth orbit, you just drop it into the atmosphere. if you're in a high orbit, like a geostationary orbit, then you would move it into what's typically called a graveyard orbit, which is about, depending on who you ask, 250 to 300 kilometer higher than the geo belt. And because I just saw in the chat, there was something, yeah, you would burn it up on re-entry. So most objects, right, unless you have something insanely compact and dense like optics, most objects or tanks, most objects burn up in the atmosphere. So that wouldn't be too much of an issue. And remember, the Earth gets, I forgot the exact number, but like 100 tons a day anyways, in terms of natural micrometeorites. So, I mean, it wouldn't be too much of a problem.
And then Gonzalo asked, do you know whether the military has considered using powerful lasers to vaporize various small debris objects?
I don't know, but I would be very surprised if the military had not considered using a powerful laser for pretty much anything. So, I mean, I think a powerful laser is a solution to a lot of our problems. No, but there have been ideas of maybe not vaporizing stuff, but basically using the radiation pressure of a laser to nudge stuff around orbit, or to start ablating or vaporizing one side of the debris object. So it basically acts like a thruster and then brings it down to Earth. I mean, there have been all of these concepts, but shooting a laser into space is also not easy. So it's a concept.
All right, one more question. John Mills says he works in a very similar lab in the industry, and so he has a deep appreciation for this work. And he asked, what's one of your biggest challenges you found in testing these systems on the ground?
Well, that nothing ever works when you need it to work. Biggest challenge. There's a lot of challenges. The biggest challenge is just simply also the complexity of the systems and the complexity of the test bed. And being a university, we cannot just outsource software development worth like a few $100,000 to some outside provider. We have to do it all in-house. And a lot of times we really have a hard time getting really reliable systems working for these kinds of things. But I mean, all these challenges are relatively easy to overcome. When it comes to the actual in-space challenges, I would really say computer vision is a giant problem in space. Getting this idea of artificial intelligence, machine learning going is a giant problem. And the dynamic interaction between two spacecraft doing the docking part, that is also something there's a lot of work needed for that kind of stuff.
All right. Well, thank you everyone for those great questions. And just want to thank you so much again, Dr. Wilde, for taking your time. Everyone, he donated his time to do this for everyone today and share all this great information with us so that we could learn something cool on our lunch break. So thank you so much, Dr. Wilde. Really appreciate it.
And again, if you are more interested, I mean, the lab website is pretty decent. We keep updating it with new material every so often. And just shoot me an email, give me a call. We can always chat about this stuff.
Okay, and I'll include in my follow-up email to the registrants your email and a link to the Orion page.
Cool.
So everyone will have everything they need. So thank you, everyone, and we hope to see you at another Lunch and Learn lecture soon.
Thank you.
Take care.